So the speaker is Professor Kimyeong Lee from KIAS. So title of the talk is Monopole Partons of Instantons. So please start.
Oh, thank you, Masashi. Thank you for inviting me to and giving me the opportunity to talk about this subject. So as I told you guys, I had many titles in my head. One was magnetic monopoles, bubbling, and another one is messless monopoles, and another one was magnetic monopole walls and fermions. But I decided to choose breaking instantons into magnetic monopoles or monopole partons of instantons. So this work is based on three works. One long time ago is Plenary, and another one recently with Duan and Namgung and Shinwang. And then third one, which appears with, I work with Shinwang and Kaiman Sun and Hichal Kim, it will appear soon. So let's start with D0 brains on D4 brains. So their instantons appear very naturally. So instantons anti-self-dual, say, configuration in SVN Yang-Mills series. And once we know the ADHM construction of, say, for K instantons, K by K matrices, PIs, and then K by 1 or 1 by K, N by K or K by N, matrix Q and Q tilde, satisfying these relations, then using ADHM construction, we can construct a gauge field. And all days, one is interested in modularized space of instantons, which is there's gauge invariance of you say for K instantons SUK, and you model out gauge invariance degrees of freedom, then there's a finite dimensional space, which is a hyperkähler space, and this process is called hyperkähler quotient. And especially if we have a SU2 gauge theory with a single instantons, then modularized space is 8-dimensional. And one can split into 4 plus 4, and 4 indicates the position of the instantons on R4, and the 4 indicates the relative motion of the instantons or size parameter, plus S3 orbit, which is S3 divided by G2. So this relative moduli space is C2 divided by G2. And this instanton dynamics appears very naturally by thinking.
One moment.
Yeah. I'm sorry. This is
Still on it.
Oh my God. I never told.
I didn't get that. Could you try?
Sorry, guys. I never use Apple, what's called? Speech, but somehow it started to appear. Let me see. Do you know, anybody knows how to turn off this?
Please, I don't know. I'm sorry.
No, I never use the Apple speech, Siri. Okay, so let me ask Siri. Turn off. All right, I never turned on, but I just upgraded and the Siri appears out of blue. All right, so sorry. So let's go to the screen. Right, so instantons appears very naturally as a dynamics of D0 brains on D4 brains. Yeah.
Yeah, could I just get clarification? So you've got the real and the complex moment map equations there. So there's, I think there's a tilde missing from the last one. Can you just give me this? Can you just tell me about the relative motion again, what you said? So you've got a zeta parameter, which is real.
Right. So let me talk about relative motion, which is that, sorry, yeah, tilde is missing here. But anyway, so 8 general modes of a single instanton, you have 4 modes for central mass. Then remaining 4 is made of the following thing. One is the size of instanton, and then another one is the orbit of the instantons. I mean, gauge orbit. So you have an unbroken SU2 gauge symmetry. So you are rotating instantons in three-dimensional space, which gives us S3, but you have only a joint method, so you have S3 divided by G2. So size times S3 is C2, then divided by G2 is the moduli space.
Thank you. So the zeta parameter was nothing to do with this relative motion.
Right. So zeta is, I was imagining non-commutative space on R4, then you can collapse the instanton to zero size. Of course, zeta is related to blow up of this singularity to finite size. I'm sorry about that. Right. Right. So this zeta parameter will be blow up of the singularity.
Thank you.
All right. So D0 dynamics on D4, if we look at dynamics on field zero and D0 brane, then basically these PIs are like hypermultiplied on D0 branes. And then this Q and Q tilde are pi-fundamental method between D0 branes and D4 branes. That's why if you have K D0 branes, which is K instantons, then pi-fundamental method will be K by N. And this ADHM construction appears as a vacuum solution of this Lagrangian, and then there is a way to construct a gauge field from this, which is Sage worked on 20 years ago extensively, and then one can write down, solving some linear equations, one can write down gauge field, which satisfies this self-duplication explicitly from these data. Right, so let's jump the instanton in arbitrary gauge group. It's toward people have worked on it. So suppose we have some SU, not just SUN gauge group, but arbitrary gauge groups, then still one can define the self-dual equations, and one can define this instanton number, which I haven't bothered to write down explicitly, which comes out to be integer, which is related to third homotopy group of this Lie group, compact Lie group, which is integer number. Now, given gauge group, one can have a dimensional group, which is all number of generators. So SUN will be n squared minus 1. And then there's a rank, which is maximally commuting variables. So SUN is n minus 1. And then there's something called the dual Coxeter number, which I'll tell you more about it later on. And then K instanton case, the number of moduli spaces dimension, which is related to 4 times number of instanton times dual Coxeter number. So if I have K instantons, they have side, and single instanton has their orientations. And if you have 2 instantons, there's a relative position plus relative orientations, and so on. So moduli space is very complicated. But 4 will be center of mass of the whole instanton configuration plus relative motion, which is 4 times K times dual Coxeter number minus 1. So this indicates that instanton 4 is universal. Then 4-dimensional space, each particle has a single irreducible particles of 4 parameter position. So it indicates the instantons are maybe made of this amount of elementary particles. And in some sense, that's true. So I'll talk about it in this talk. Right. So let's look at the arbitrary gauge group. They're all classified, and there are SUN type, which is AR. And I just wrote an extended thinking diagram where you have a white dot is the lowest negative root. And then thinking diagram captures the gauge algebras. And there's SO2n plus 1, which is PR, and SP2R, USP2R is CR, and the SO2R is DR, and E6, E7, E8, G2, and F4. Now, dual Coxeton number is the SUN case n, which is so AR will be R plus 1, and SO2n is SON is n minus 2, so this one is SO2R plus 1, so it's 2R minus 1 and 1. Dual Coxeton number is related. That's simple root of the Lie algebras, and dual Coxeton is related to dual root of this simple root. Right. So as I said, if we have k T0 branes on n T4 branes, the instanton they appears as a k instantons on SUN gauge series, and the fixed on T4 brane is 5D n equal to 2 super Young theory, which is maximal 16 supersymmetry with KG group SUN, and so you have n equal 1 vector multiplet and then n equal 1 hypermultiplet. And this theory, if we have instantons, then one can define the instanton current, which is dual of the F as F trace. And then instanton mass for KG coupling constant 1 over G5 square is given in terms of A pi square or G5 square with some of SUN case. And now, interesting thing is that T4 brane appears as M5 brane wrapping a circle from M theory perspective, and T0 brane is Color-Klein mode. And so T0 brane, so X5 direction is periodic, it's circular with 2 pi r, radius R5. And then Color-Klein KK momentum is integer divided by R5. And instanton mass from K theory side is A pi square over G5 square. So Cyborg have noticed that if we go to strong coupling limit, then R5 square goes to infinite, which means compactification radius of the M circle goes to infinite. So you go to 60 theory. So 5D Yang theory is not usually non-renormalizable, but in strong coupling limit, in very short distance, there's a hidden UV convolution, which is 60 2,0 series. So this is A-type 60 2,0 superconformal field series. Wrapping on a circle becomes 5D SUN gauge theory, maximally supersymmetric theory, and also compactification leads to Color-Klein mode, which becomes instanton in 5D theory. So it's amazing sort of relation between 6D theory and 5D theories. Now, if you look at 60 2,0 theories for an NM5 branes, then it's interesting. It's not gauge theory. So if we split the NM5 branes, which is called instead of Coulomb branch, it's called tensor branches. On each M5 branes, there's no photon. Instead, not like a T-brane case, there's a tensor multiplet. So this is n equal 1, 0 tensor multiplet, and then there's a hypermultiplet. Now, this 2-phone tensor field, B mu, has 3-phone tensor field strength, and it is self-dual on the epsilon tensors. So which means this theory is both electric and magnetic. And the M2 branes connecting to M5 branes are sources of this B mu field because it's a string. And because field strength is self-dual, it means it's self-dual string. So it's not electric, it's not magnetic, it's both electric and magnetic. And turns out this Topological theories, besides this A-type coming from NM5 branes, there are 3 types of theories: A-type and DR type and E-type, E6, E7, E8. And those another way of getting by compactifying, thinking about type 2B theory on C2 divided by SU2, finite subgroup of SU2, which is ADE type. And this strange theory is non-Lagrangian and is purely quantum theory, as is both electric and magnetic at the same time. And also, if from various calculations, the degrees of freedom is not proportional to dimension of Lie group because it's not gauge theory. Rather, it comes to product of the dual Coxeton number times the dimensional group. So SUN gauge theory, dual Coxeton number is n, and the dimensional group is n square minus 1. So it's n times n square minus 1. which grows with n cube in large n. So this growth of the degrees of freedom is much faster than n square. And of course, we have to ask, what do you mean by degrees of freedom? We don't have time for that, but I'll mention briefly something about it. Right. So again, we are wrapping the theory. Instead of going to the sixth dimension by going to strong coupling limit, we can wrap the T0 brane on circle. And then 5D theory wrapping on the circle, then because it has 16 supersymmetries, in low energy, we have an n equal 4 supersymmetry, 4D n equal 4 supersymmetry Yang theory with SV engaged group, plus various Kalachek-Klein modes. And when we are compactifying these x4 directions, we can tilt along the x5 directions such that we can have theta parameters appearing. And if theta equal to 0, then Yang coupling will be f square divided by r5 square times the compact direction, which is 2 pi r4. That will be a 4D coupling constant, which is dimensionless, and it is. And then if you look at fine structure constant alpha 4, which is G4 square 4 pi, then put this into relation, then we use the relation 4 pi square over R5 square is R5, G5 square is R5, then we get the fine structure constant 4D theory is just the ratio between R5 and R4. So S duality, which we expect in 4D theory, which is between strong and weak coupling duality, which is exchanging electric and magnetic charge object, is basically alpha 4 going to inverse of alpha 4, which is going tau going to minus 1 over tau. And that is basically ordering of the compactification. We compactify the 6D theory to 5D, then compactify further to 4D, but we change the ordering, then we get the S dualities. So sometimes we have self-dual string, wrapping the fifth direction, then it becomes W boson. Wrapping the fourth direction, if you don't wrap it, then it becomes in 5D monopole string. Then you wrap the R4, then it becomes a magnetic monopole in 4D. So exchanging these two is exchanging W bosons and magnetic monopoles. Now, when we compactify this 5D Yang theory to 4D, we get a gauge holonomy, which is the expectation value of gauge field along the, and this expectation value, we're using the large gauge transformation and the ordering while symmetry, so we can order in such a way as decreasing order. So those VI is basically, from T duality perspective, T4 brane becomes T3 brane, and T0 becomes T1 string wrapping the dual circles, and the T3 brane position on dual circle is given in terms of these VIs. And then one can define the simple root, which is just the distance between next two these three branes next to each other in this order. And then there's one more root which goes around the circle, and that's called the lowest negative root, because if you this simple roots are positive, and then this sum of this with minus, so this lowest negative root, and then T1 string connecting these three branes become fundamental magnetic monopole, which has 4-0 mode with magnetic charge given in terms of dual root, and mass given in terms of this dual root times expectation value of a field, and then is given by and this one is some sense because of A4 is sort of a scalar field, so this is a sort of instanton number carried by these fundamental monopoles, and because their sum is equal to 0, and those are simple root, I mean simplest groups, so dual roots are same as itself, and then total mass of this monopole is that because Vn plus 1 is V1 plus 1 over R, is exactly when you sum them up, this monopole mass, then it becomes instanton mass. So you can see instanton is split into m pieces. Each one of them has 4-0 mode. So total instanton has 4n0 mode. And even though each monopole carries fractional instanton charges, total instanton charge will be 1. So that's fractionalization of instanton to magnetic monopoles in simplest way for SU engaged groups. Right. So as I said, one can think about different engaged groups. So in this case, one could ask, suppose we start with 5D theory with any different gauge groups, and then we have instantons. Then we would ask, as circle compactify, how they get splitted to magnetic monopoles. So for any group without twisting, circle compactify, then they have holonomies, and the condition is that this when you have dual root is 2 alpha I divided by alpha I square, and the dual root times expectation should be zero, positive, and also 1 over alpha plus lowest negative root has to be positive. And there are 4 fundamental magnetic monopoles for each simple root with 4 zero modes. And here for non-simplest groups, for example, Comac, which are non-negative integers, are defined such that when you sum over all the dual root with Comac's productive is equal to 0, and the lowest negative root, Comac, is equal to 1. And then dual Cox number is the sum of these Comacs. And indeed, so we have so fundamental monopoles for each alpha I, then we include the number of this fundamental monopole for root I to be number given in terms of Comacs, and then total number of zero mode will be exactly given in terms of through this definition of dual constant number, same as the one we expect from instantons. 4 times dual constant number is given in terms of 4 times sum of the Comacs. And for K instanton, you just multiply them. So as far as zero mode is concerned, it is made of the this fundamental monopoles, and also mass term, if you calculate it, and it's exactly given in terms of the monopole mass we expect. And so again, for any gauge groups, if we have instantons, then the number of zero mode is 4 times K times dual constant number, which is made of the 4 plus 4 times this difference. And the 4 is again center mass, and the rest of it is the relative motion of the magnetic monopole constituents. Turns out there's different factorizations or splitting of the fractionalization of the instantons, which people haven't explored much. And I explored a little bit, but still it's very mysterious, and I want to draw attention from you guys. And this is that suppose if I have a single fundamental string wrapping a circle n times, then length of the effective string is n times bigger, because it's a single string wrapping circle n times, which means KK momentum is really not 1 over radius, rather 1 over n times radius, because the string is bigger, and the KK momentum is living along the string. So you can see that KK momentum got fractionalized by 1 over n of the standard KK momentum. And this has been explored in various contexts for fundamental string partition functions. And now one could imagine if we have n M5 branes in 6D theory, which is two-comma theory, and then remember T0 brane is when we circle compact by M theory, then KK momentum along the M circle is the T0 brane. But if I think about the single N5 brane wrapping the circle n times, then again, KK momentum leaving on the NM5 brane would have a momentum less than 1 over R. It'll be 1 over n of the KK momentum. So you can see instanton number got fractionalized to 1 over n right away. So it's, but also instanton KK momentum will be 1 over nr, it's not like a monopole fractionalization where depending on value of the Coulomb parameters, it will be different, but it's very uniform. So for example, if I have 5 M5 branes, I can have a single M5 wrapping 3 times, another one wrapping twice, then fractional KK momentum will be 1 over 3R or 1 over 2R, whatever notation, the summations. But total, of course, KK momentum has to be integer divided by R because it knows about but this circle being radius, just compactable circle. So this part of fractionalization hasn't been explored at all, and I don't know what's the implication of this from the two-comodulus theory perspective or from a different perspective. But this is very interesting directions. Now, there's one more direction which I don't have time for, but D0, D4 brane, one can introduce fundamental string, then they form a super tube. Probably you heard many years ago by Paul Townsend describes super tubes, and they arise from the dionic instantons. So as I say, KK momentum on two-comma series instantons. But if we think about self-dual string, which wrapping the circle becomes a fundamental string connecting D4 branes like W bosons, and those arise from the self-dual string wrapping the circle. Then KK momentum along this self-dual string is a wave on a circle, and taking carry also as it go around, it can carry angular momentum along the 1-2 direction and 3-4 direction and other directions. And then from D0, D4 fundamental string pulls the D4 brane to the 1 point, but D2 brane circle appears as a Myers effect, and the 2 D4 branes are not meeting at the 1 point, but along some tubes. And on this D2 branes, D0 brane becomes a magnetic field, and fundamental string becomes the electric field, and the pointing vector pointing, there's PT, maybe PITY. There's momentum going around the D2 branes and generating angular momentum along the J1 and J2. So quantum calculation of this dionic instanton generate the class of partition functions. So again, there's D2 branes, and then D0 branes become magnetic field, and fundamental string becomes electric field. Then E cross B generate this angular momentum along the tube. And also this shape is basically if we have sine wave along the string, and then this is moving not just plane, but various directions, then they can form a circular frozen wave on D4, and that is super tube, which can take any shapes and still remain in BPS. Okay, so let's think about twisting two-comma theory on a circle. In 60, two-comma theory comes with ADE type. So if we compactify on a circle, then we get a 5D Yang-Mills series ADE type with a simplest group. So we have to get the twisting of this non-Lagrangian theory to get the 5D Yang-Mills series with non-simplest group. To do that, let's think about the twisting of 5D theory to 4D, which is gauge theory, and in this case, the twisting is quite standard. So the twisting is done using auto-automorphism group of the thinking diagrams. So for example, AN type is just without extended thinking diagram, is just nodes with line, then there's obvious G2 symmetries. So when you compactify from 5D Yang-Mills series to 4D, on the G2 symmetry, if it's even, then it will be on the KK momentum will be integer. But if it's odd, then this sigma is eigenvalue of this auto-automorphism, and then it will become half integer KK momentum, and so on. So if you have SU, say SU4, then there's SU4 is made of 3 nodes, and there's a G2 auto-automorphism. And then SU4 after that is made of even long root and short root of the USP4, and the long roots get the KK momentum, which is basically part of the root, and then short root get a half KK momentum. So K over 2 KK momentum, so it can be case even, then together they form a CR root, and the other part is antisymmetric representation of USP4 for SU4 case. Now, SU5 case is more complicated. Zero KK momentum has together USP 2R, and then you have singlet, and the antisymmetric hyper becomes half KK momentum, and then fundamental can have 1/4 or 3/4 KK momentums. Now, so
what
those
is
are
K?
K is
You've
KK
got R
integer.
on one side. What is K?
K is integer, which tells the KK momentum. So so K is integer. So let's look at the if it so this is all long root appears to all the integer KK momentum, and short root appears as integer and half integer KK momentum, because it's case even or odd, it can be integer or half integer. Now, this case, special root is like fundamental representation of USP, and then in this case, the fundamental representation can carry 3/4 or 1/4 KK plus time plus integer KK momentum, and singlet, and also from here you have antisymmetric representation. They can have half integer plus integer KK momentum. That's what it means. So it's a very nice way of splitting generators, and this twisting doesn't spoil any D algebras, and that's why it's a way to get theory in lower dimensions.
Thank you.
So you can see all the non-spliced group, we can get it by twisting 5D Young series. Of course, there's a two USP2R, there are two differences, this guy and that guy. And turns out this is related to 4D unequal four supersymmetric series USP2R. There are two types of that. On the long end dual, this CR and BR are dual to each other. But this guy is self-dual on the S dualities. The reason is the theta term here is 2 pi. USP2R theta, range of theta is now from 0 to 2 pi, is 0 to 4 pi. And the 2 phi case is self-dual on the S duality, which is rather amazing because long becomes short root, but short root monopole is dionic because theta term is 2 pi, and is half of the W boson electric charge. So you need two of them to make monopole to be matchless. Monopole to be to carry no electric charge, which means again it becomes a long root. So that's why it's self-dual. Right. So here is the folding. This is the, if you look at the thinking diagrams, then you can see the arrow is pointing that way. So even though it's not quite true, if you change the arrows, then you can see it's self-dual. And this is dual to the nonsense, so which I'll show you later on. So twisting of the this type leaves that, and twisting of G2 twisting is these diagrams, and D4 divided by G3 leads to G2, E6 divided by G2 leads to F4, and so on. And interestingly, even when we do twisting, again, there are simple roots corresponding to this extended thinking diagrams. And again, with low energy is reduced rank. And then we can define the dual Comax using co-root. And also one can see that lowest root, P0 is equal to 1, and dual Cox number turns out defined from this twisted case turns out to be not changing after even though rank of group is reduced. So that if you have instantons, G2 twisting doesn't reduce the number of the zero modes. So they are invariant under this twisting of the ordinary Lie groups. Now, n equal 2 super Yang-Mills theory of different group comes in 5D. Remember, we got this non-split group from 4D from the twisting of the 5D ADE series. So to get this non-split group in 5D, we have to twist the 2-zero series. And that's exactly changing the ordering of the twisting. Instead of untwisting and twisting, we have to twist it and then untwisting. So we have to make a S-dual transformation of that. So we have this twist series, and then we make S transformations, and then we get the which becomes 5D non-split group or compactified on a circle. So this self-dual case, if you go to 5D non-split S-dual, then we go to 5D, then that becomes n equal to USP theory. But USP theory has discrete zeta in 5D, and it can be 0 and pi. And this is exactly the case with pi, and one can chase the oriented fold, and we get this. Now, for this case, again, we get for the CR type, but S-dual is BR, and then we get a 5D SO2n plus 1. And this one leads to BR, but we go to S-dual, then it's a USP6 and a USP-R, and then we USP2R, then we get a 5D USP2R. And D4 case, we is self-dual, so we go to 5D G2. And E6 case, for example, we get a 4. Now, twisting of Tokamak theories, we have self-dual. So S-duality in 4D is basically changing the ordering of the configurations, and 5D group has been obtained using S-dualities. Now, one thing, as we explore the various partition functions and so on, we found during the twisting from 6D to 5D, one can have degrees of freedom preserved because we are looking at short distance physics, and this twisting is along the sort of boundary conditional circle is long distance physics. So from which we found this amazing formula, which is that suppose original theory dimensional group times dual constant number, and then you divide by order of auto-automorphism with some caveat. Then that becomes this theory we obtain from the S-duality, ordinary twisting with S-duality. So then dimensional group times dual constant number. So this is very different from the preservation of the dual constant number under the twisting. It's a completely different thing. Now, so let's look at the SU6 case, A5 type in 60. Then ordinary twisting would have led to USP6, but instead, USP6, we get an S-dual, which is SO7. So if we compactify say physics on Tokamak theorem 6 and 5 lanes, then twisting it leads to 5D SO7 Yang-Mills series. Now let's look at this product. Dual constant number where SU6 is 6, dimension is 35, then order of auto-automorphism is 2, divided by 2, then you get 3 times 35 is 3 times 5 times 7. Now let's look at SO7. Dual constant number is 5, and then dimension is 21, so it's 3 times 5 times 7. So you can see it's equal, and so on. For SU7, turns out that dual constant number is 7, then dimension is 48, 7 squared minus 1, 48. In this case, we have to divide by 4 because there was G4 involved, so we have to divide by 4. That's natural scale. Then if you divide by 4, then 7 times, SU7 7 times 48 divided by 4 is 7 times 12, which is 3 times 4 times 7. Now, in this case, I said it's same, what is it, twisting of same thing. So we get a USP6. So USP6, dual constant number is SP6. USP6 is SP3, so it's 4, it's a 4 dual constant number. And USP6 dimension is 21. So it's USP6 is right 21. So it's 4 times 3 times 7, and SU7 is 7 times 48 divided by 4 is 7 times 12 is, so it's same 3 times 4 times 7. So you can see this invariance of degrees of freedom between original 6D theory of AD type and then using auto automorphism. Then we get this Langland dual of the ordinary twisting, and this turns out to be true for all the cases. And this is a very simple relation, and here's the dimensional growth and dual constant number, and you can go through all the twisting, and it's true all the cases. So we've been asking mathematicians for last 2 years, because this was discovered about 2 years ago, everywhere, and looks like they haven't seen this relation before. And so I would say string theory have provided a bit of this interesting relations. There's also a relation to Weil vectors. Weil vector square turns out to be equal to 1 over 12 times dual constant number times dimensional group, and it has additional context, which I don't have time for. Right. So recently, I've been thinking about 2,0 and 1,1 little string theories and the twisting of these theories, and that led to again additional relations between additional way to look at the fractionalization of instantons. So little string theory is a little different from 62,0 conformal field theory, which is quantum field theory. But little string theory is theory on this maximally supersymmetric case, theory on NS5 branes, and it has T duality, so it's not quantum field theory, but it doesn't have gravity. So it is theory living between quantum field theory and string theories. And there are lots of them in 6D. There are this maximally supersymmetric case, and there's 1,0 little string theories, and they have all kinds of varieties, and they have all kinds of interesting structures. So here we'll just focus on maximally supersymmetric case. And again, like 2,0 superconformal field theories, there are only 3 types, A, D, E types, which is constant in 6D. Now, again, 2,0 A types little string theories, instead of M5 branes, we look at the M5 brane with M circle compactified, which becomes the NS5 brane of type 2A string theory. So instead of a straight line where M5 branes are lying down, M5 branes are positioned along the M circles. Now, little string theory has a string, little string, which is fundamental string, which is in this case M2 brane wrapping the M circle, becomes fundamental string from type 2A perspective, and it becomes again fractionalized because you have M5 branes, and then M2 brane connecting each M5 branes self-real string, and basically again one can write down in terms of this fractional M2 brane or fractional fundamental string is W boson, so we can write in terms of simple root, and that their sum is equal to 0 because of that total electric charge is equal to neutral, so it should be 0. And again, SU n case Comac is 1, and this shows that again fractionalization of the M2 branes into fractional self-real string or fundamental string into fractional fundamental strings. So 2,0 theory A type is basically string theory on NS5 branes, and with GS coupling constant goes to zero limit, the gravity decouples and is constant 60 string theory. You could ask, ordinary quantization of strings leads to critical dimension 10 or 26, but that quantization assumes that string is interacting weakly, but these strings are interacting very, very strongly because, again, fractional part is a self-deal string, and the interaction coupling constant is 1, so you cannot do standard quantization of strings. Now, 1,1 A-type little string theory is, again, NS5 branes in type 2B string theory. Then in which case, if you use SDL, then NS5 brane in type 2B becomes the NT5 branes. And you can see on NT5 branes, there is a 60 Yang-Lee theory with supersymmetry 1,1, which is dimensional reduction of SVM case theory intended to 60. So 60 1,1 super Yang-Lee theory with KG group SVM. Of course, that's UV incomplete, but remember, in 5D theory, if we go to strong coupling limit, then we have 62 little super conformal field theory, which is UV complete. Now, 60 1,1 super Yang-Lee theory, UV completion is little string theory instead of the ordinary quantum field theories. And instanton string, now, because our spatial direction is 5-dimensional, we can have an instanton along the 4 directions. So as we engage group, then there's one more direction. So it becomes instanton string instead of instantons. And this instanton string, from D-brane perspective, is we have NT5 branes, and then we have a single Dian string, which is instanton string. But because we make S-dual transformation to NS5 brane, then it becomes fundamental string. So this type A 1,1 little string theories, and they are T-dual to each other because when we compactify the theory on a circle, NS5 brane is dual to NS5 brane, and the fundamental string becomes KK momentum, and KK momentum fundamental moment string. So you can see that here fundamental string got fractionalized, and here KG theory, when we compactify on a circle, we can turn on the KG holonomy, then KK momentum becomes fractionalized. Right. So as I say, Tucumadiero little string theory on circle of radius R5 is equivalent T-dual to 1,1 little string theory on a circle of dual radius R5 tilde, which is LS squared divided by R5. And 1 over LS squared is basically string tension of fundamental string. And the instanton string in 1,1 little string theory on a circle, because as we can turn on the KG holonomies, again, when we do the same analysis as what we did before, it becomes magnetic monopole strings. So you get decomposed into magnetic monopole string, and for AD group, number of fundamental monopole string will be given in terms of the comarks, and for each fundamental monopole string, and total number of this composition will be dual Coxton numbers. So as I said, T-duality is relating momentum to winding and winding to momentums. And the Tucumadiero wrapped self-dual string becomes 1,1 momentum, but both of them are fractionalized. And Tucumadiero integer KK momentum becomes 1,1 instance of string wrapping a circle, so which is string wrapping a circle is always integer. Now, we all know the T-duality with twist, and the lesson for twisting comes from Tucumadiero super conformal field theories. So we did thing of the A-type, then we get theory we want. So depending on even or odd, we get different branes, and we have a long how it's folded. We get a discrete setup for USP type and so on. D-type we fold it, and we get O for minus, and we get this top of the type of the thinking diagrams. So we first ask 1,1 Yang-Mills theory has a non-simplest group B, C, C prime, G, and F. So you would ask Tokumadera theory only comes with ADE type. So you have to get this non-simplest group, similar to what we have in 60 to 5D twisting, which led to interesting relation between product of dimensional group and zero-Coxeton number. But this is completely different because this is a non-simplest group in 6D, not 5D. And then we have to obtain this from twisting of the Tokumadera little theories. Turns out, of course, we have non-simple case rule. So BR, CR, and the CR turns out to be before twisting circle compactification. I mean, so this theory, we compactify on a circle without twisting because it's non-simplest groups. There is no outer automorphism. So we get this theory by just compactifying, but in 6 also discrete setup of USP theory can be 0 and 2 pi. Now, so then using the lessons, we go back to Tokumadera theory and we ask what kind of folding we have to do get these non-simplest groups. And there's a geometry of this less intuitive, but this thinking diagram plus oriented folding give us the answer very clearly. And the geometric approach has been done by Del Dotto and also others. So by tracing detail of the folding, we can see that this type of folding of as a 4 gauge group by G2 leads to this thinking diagrams and so on. So we can discover all the Tokumadera theory, which comes in rather complicated way. But again, at the end, we get the answer. Now, remember that Tokumadera theory is if you have a single fundamental string, you get fractionalized. And so this original theory, zero-Coxeton number is, because it's SO4R, D2R is SO4R, 4R minus 2 is the zero-Coxeton number. And that's the way fundamental string is fractionalized. Now, when you do twisting, we are folding, identifying some of these fractional strings. So we divide by 2, then we get this folded theory and zero-Coxeton number of this 61,1 theory, and see exactly matches. So again, G2 twisting, we divide by 2, then we get that. Divided by zero-Coxeton number of this guy, then we get this. And this case divided by 4, because it's G4 folding, we get a G2 cross G2, then we get a zero-Coxeton number. And G2 E6 divided by 3, F4 is E7 divided by 2. And you can see this is a rather interesting folding because this is not outer automorphism group, because outer automorphism group or Lie group is outer automorphism on thinking diagrams, not on the extended thinking diagrams. And this extended thinking diagram for Tokumadera little string theory is not really extended thinking diagram. They are more or less equivalent in the sense that this is not ordinary Keck-Smoot algebra. This one has KK momentum, but this theory doesn't have, this one doesn't have any KK momentum. So it's, even though same diagram, it captures a different split. Now, 1,1 little string theory can be simplest AD type, but you can have outer automorphism. So we can do twisting, like when we did it from 5D to 4D, we can do 6D AD type to 5D twisting theories. So, for example, A2R type of twisting of the 1,1 theory, and we have to have a corresponding Tokumadera theory, and you can see it's much more complicated. So in this case, the zero-Coxeton number is 2 times 2R plus 1, but we divide by 4, then here we had the G2 twisting. So we multiply by 2, so we just divide by 2, then we match this. And also each case they work together. And so we can get all the twist theories, and it shows clearly how one can fractionalize the instanton string, which is from S version is fundamental string into monopole strings, and each node represents a monopole string, and the whole zero constant number represent the instantons. Okay, so to conclude, so instanton can be fractionalized into magnetic monopoles, either placed in 4D Yang-Mills theory or 5D Yang-Mills theory on a circle. I didn't have really time for what happens from 4D Yang-Mills theory, where instanton plays a role of tunneling, then compactify on a circle, then it becomes magnetic monopoles. They represent again 3D tunneling phenomena. Also, by considering little string theories, we have shown instanton strings or fundamental string can broken into monopole strings on the circle compactification, and twisting, again, one can match both sides very well. And we have studied partition function or the class of partition function involving monopoles and instantons. Sorry, again, instantons. Having considered, but I didn't have time to present here. And also, PPS quivers on little string theory on this is rather interesting directions on little string theories, but okay, I don't have time. So, and also as I mentioned at the beginning, there are something called messless monopoles whose presence, which cannot exist by its own, but it can exist with some massive monopoles around, and they are also related to magnetic monopole bubblings. And so there are questions arising which I haven't addressed. So PPS on little string theorem, 4-dimensional cross T2. What I mean is, so if I think about 5D n equals to 5D theory, we compactify on a circle, then we had this magnetic monopole, instantons, fractionalized magnetic monopoles, and W bosons are W bosons. But we can turn on the mass term for the hypermultiplet, then your supersymmetry is broken from the n equal 16 to 8 supersymmetries, in which case, using Cyborg-Eaton formalism, W boson get fractionalized into tions and monopoles. Both of them become hypermultiplet, not a vector multiplet. So then this fractionalization of the W bosons lead to also all additional effects. So instantons get additional further fractionalizations. KK momentum is represented by D0 brane get fractionalized and so on. So there's a PPS quiver of the this particles describing these fractionalized systems. And also there are monopole walls and fermions, which I wish I have more time to explore and talk about it. And hopefully Cherkis may talk about periodic monopoles, which will overlay with monopole walls. And then there's also magnetic monopole string junctions, which can be oblited to self-adjoint string junctions. And these junctions are related to Kaplan retifications and so on. So those are interesting directions. And also, I recently probably used, there are a lot of activity on magnetic monopole instantons in 3D, and they play a role of hypermultiplays, and it changes all the long-range phenomena of the 3D physics. And the people have been exploring these endless variations. And still, I feel that there are a lot more to be explored, like even Coulomb phase and Higgs phase for n equal 4 supersymmetry theory as a magnetic monopole playing an important role. So let me stop here. Thank you.
Okay, thank you for very interesting talks.